So now we're moving on from projectiles onto net forces. This two-page little piece of notes here, it's really a review from Physics 30S. We just did projectiles, and if you recall, the free body diagrams for projectiles are pretty straightforward. The only thing we have is the force of gravity downwards. So here I have a list of different types of forces. In fact, now that I'm looking at it, I'm going to add this T as well. So just as a quick review of what these different forces are, Fg here is equal to mg, and this is known as the force of gravity. Sometimes instead of, oh, that wasn't very good. Sometimes instead of writing Fg, just because it's so short, I sometimes even write mg instead. So for example, for a projectile, you'll see sometimes, mg just as quick to write the formula for force of gravity as it is to write Fg, force of gravity. So m is the mass and g is the gravitational field strength, or the acceleration due to gravity, depending on how you want to define it. So close to the Earth, it's 9.8. So in our questions, we're going to be using 9.8, unless sometimes I tell you to use 10 just to keep things really simple. The net force here, F net, is equal to the sum of all the forces. So here we can write net force, or another way of saying it is the sum of the forces. And we can, sometimes you'll encounter the same thing. You'll see this Greek letter sigma. Oh, I'm not doing a very good job of that. Let's try it again. Sort of like that, which is a sigma, which means the sum of all the forces. So in some textbooks you might see something like that. Fa is another way of saying the applied force. Ff is the force of friction. We have a formula for force of friction. Ff is equal to another Greek letter, mu, multiplied by the normal force. Now, mu here is known as the coefficient of friction. Coefficient of friction. And Fn here, I already mentioned, is what's known as the normal force. Now the word normal actually means perpendicular. Okay, so this actually means perpendicular. So for example, if we have an object that is on a horizontal surface, this horizontal surface is pushing back on the object. So although there is a force of gravity downwards, there's a normal force. You can think of it as the surface support force in a way. Now if that surface happened to be on an incline, again it would be perpendicular to the surface. So perpendicular, here's a symbol for perpendicular. So in this case the normal force would be that direction. So that's the first thing to remember about the normal force, is its direction. Also, it is not always, I'll put in a new color here, not always the same or not always equal to force of gravity. Quite often in grade 11 we get used to it being the same as a force of gravity. Today we're going to encounter a few examples where it's not. T is equal to a tension force. So you get a tension force with strings, cables, I don't know, dog leashes, or dog chains, I don't know, all those types of things. Yeah, you can think of it as kind of like an applied force, but it's with a string. Alright, so here's an example. Let's try a couple here. It says, when adding forces together, sometimes it's helpful to resolve a force into two components. Here in this question it says, what is the acceleration of this object? Well, to figure out the acceleration, we know that F net is equal to ma So quite often here I'm going to start off by saying then A is equal to F net divided by m. So if we can figure out these two simple things, what is the net force and what is the mass, we can divide the two and we'll get our answer. So first of all, to do our net force, we have to add all these forces together. Well, three of them are kind of playing nice with each other, and this last one is a little bit funny. In the applied force, here it's F app, but it's really the same thing as the FA that I was talking about before. So perhaps someone is pulling this object. If this was either horizontal, going straight to the right, or if it was vertical, straight up, it'd be so much easier to add these together. So what we're going to do is we're going to do what was mentioned up here. Resolve the force into the two components. So I'm going to take this applied force, I'll redraw it here. So this is 80 newtons. Here, I'll zoom in a little bit. Here, that is 80 newtons. And this angle here is 30 degrees. So what I'm going to say is that this would be the x component. So I will call this FAX. And this will be the y component, FAY. And remember that this is my FA, the 80 newtons. So FAX is going to be equal to 80 multiplied by the cos of 30 degrees. And when you get your calculator out, I think that's about 69.3. And FAY is going to be 80 times the the sine of 30 degrees. And so you just remember how x goes with cos and y goes with sine, and we should be good with this. And so here the sine of 30 degrees is a half. So we get 40 newtons. So what we're going to do is we'll redraw this, and wherever we saw this, we will replace it with the two components. So maybe it's time for blue now. So here we get our original object, and we've got this 58 going up. That's the normal force. And then I've got this FAY, which is 40. And I've got this force of gravity downwards, which is 98. I guess I could be writing in what they all stand for. Let's just stop for a second. So we've done all our vertical ones. 58, see if I can make that look better. I've done all my vertical ones, and you can see that the 58 and the 40 add up to 98, and then there's a 98 going down. So right now I can say that vertically the F net, the forces cancel each other out. And it kind of makes sense, because I'm guessing if there is a normal force, it's probably a situation where there's an object and it's being pulled along by some applied force like that. So if it is accelerating, it's probably going to be accelerating to the right. So in other words, all the forces added up together are going to be to the right. Let's add our last ones. We've got FAX, which goes to the right, which is my 69.3. And I do have a friction force, which is going the other way, which is 40. And again, I could label them all, but I've already labeled them once, so I think this is fine. So now if I add them all together, which is my F net, well, my vertical ones cancel out, so I really just get 69.3 minus 40, all divided by the mass. Now I have to go and figure out the mass. So you may recall that the force of gravity here, since it's equal to 98, the force of gravity is equal to m times g. So if I put in a 98 here, is going to be equal to m times 9.8. So when I divide both sides by 9.8, I'm going to get a mass of 10 kilograms. So over here I'll get 10 kilograms. 69.3 minus 40 is 29.3. Divided by 10, it's going to be equal to 2.93. Most of my numbers are only two digits, two significant figures, so I'll round it off to 2.9 units, meters per second squared, and direction, which is to the right. So here I've answered the question about acceleration. Okay, so we did those. We did, I think, a fair number of those in grade 11, so it's a bit of a review. I would like you to try this. This is a very similar example. So hit the pause, give this a try, and then come back and see if you did it right. Okay, so I completed the answer here, and hopefully you had done the same, and our answers are pretty close to the same. So I took that 100 newtons and I changed it to that's x and the y components, and I redrew it. So the idea is I'm replacing my original vector with these two, the x and the y components, because this is the same thing as this and that. And once I've got this drawn together, I notice once again that my vertical components all add up to 0, because 174.3 and 70.7, that adds up to 245. So vertically, it is not accelerating. Horizontally, the F-net will be 70.7 minus 40, and then when I divide that by 25, I get 1.2 meters per second squared right. So hopefully you did okay on that. Let's go take a look at our flip side. It says, be careful about the normal force. Okay, so here's an example of a cart being pulled to the right. So if we were to draw a free body diagram for that, maybe in this case we'll draw this as a tension force. Maybe that's a string. In this case, the force of gravity downwards would be the same thing as the normal force upwards. And why is that? Well, if this is accelerating, it's only going to be accelerating vertically. In this case, there will be no vertical acceleration, and that's exactly what I write in the note down here. I said, if there is no vertical acceleration, for example, an object that's sliding along a horizontal surface like this, then the sum of the vertical forces must equal 0. So there's a pretty easy example. But what if we change this, and what if we said, okay, instead of having this rope being pulled this way, we had the rope pulling upwards like that. So that would change our diagram, and now my tension force would be up to the right. And I would still have the same force of gravity downwards, because the mass hasn't changed, but actually what would happen is the normal force would decrease. So why is that? Why would it decrease? Well, just like we did before, we can take that tension force and we can replace it with its x and its y components. So I can go and say, all right, this pulls a certain amount to the right, so that would be the x component, and it pulls a certain amount right, so that would be the y component. So I kind of like either writing the original one or the components. I don't like having them both on there at the same time, because the tx and the ty represent the same thing as this original one, just resolved into its components. So now I've kind of I've deleted the original tension force and replaced it with the x and the y. Now I can see these two vertical forces added together are going to add up to the force of gravity. So sometimes the normal force is not equal to the force of gravity, and that is one example. So here I said, oh, well, here is, I think, our example from the your turn, I think it was, the 70.7. See, where was that? Yeah, right here. This is the your turn example, and here's another example where the normal force is not equal to the force of gravity. Over here I write, well, F net is equal to ma. You can also think of this as happening in the x direction and the y direction. In this example, the sum of all the y, the F net y, is going to be equal to 0. So right here we would be saying this would be 0 is equal to this mass times, there would be no acceleration. So if you realize that there's no vertical acceleration, so if you realize that this is the case, then we know that the vertical forces are going to add up to 0. So the normal force is going to be whatever is kind of required in order to make sure everything adds up to 0. So if the object is sliding on a horizontal surface, you know that F net is equal to y and the vertical forces must balance. Okay, so we've got one more example here that we can solve together, and then you've got some similar ones for homework. The homework is a worksheet, and there's also a sublevel, a MOP sublevel to do. Okay, so let's try to fill out these blanks. I think it's one of these examples where we can kind of hunt around here and see which one we can do first. Pretty straightforward one to start off with is if we're given the mass, then we can figure out the force of gravity. So in this case I'll do 98 newtons because it's merely 10 times 9.8, so I got that 98. The normal force will not be equal to 98 because this does have a vertical component. Well, maybe we should do that one next. So we'll say, okay, if this is 60, Then this will be my FAX, and this will be my FAY. FAX will be equal to 60 multiplied by the cos of 30 degrees, which is equal to, I think, 51.96. And the FAY will be 60 multiplied by the sine of 30 degrees. Again, the sine of 30 is the nice half, so 60 times a half is equal to 30 newtons. So I'm going to draw this here. I'll say this is my FAX is going to be equal to 51.96, and my FAY is going to be equal to 30. And I'm going to kind of like try to ignore that arrow because I've replaced it with those two. Well, I've got this downwards arrow, which is 98, and I've got one upwards arrow that's 30, so 98 minus 30 is going to be equal to 68. So I know that the normal force is 68. Here's the first time now, in the other questions they gave us what friction is. In this case we're going to have to calculate what friction is. So FF, and this is on your formula sheet, is equal to mu times the normal force. So this will be equal to 0.3 multiplied by the normal force of 68. When I check that out, I think I get 20.4 newtons. So I'll write this one out, 20.4. And what do I have left? Well, I can figure out what my F net is. So F net here is going to be equal to, well, my vertical forces add up to 0. In fact, I made sure that that was the case. I calculated the normal force so that everything would add up to 0. And I've got a rightward force of 51.96 and a leftward force of 20.4. So the F net will be 51.96 minus 20.4. So that would be equal to 31.56. I'll keep a whole bunch of digits until I'm at the very end. My acceleration then will be this divided by 10. So really the decimal gets moved over. And instead of writing 3.156, it seems to me that there's a lot of two-digit numbers here. So I'll round it off to 2 digits and I'll say 3.2 meters per second squared. So this might be an example where that was the final answer that we're looking for. Okay, so now it's your turn to work on that homework there, and really this worksheet has a bunch of these style questions, and I think for those of you that did grade 11 with me, it should look kind of familiar. All right, I'll see you in class.